Greetings, Panthers. Dr. Augustine. Today we're going to look at the last section of Chapter 6, and this deals with real gases, or in other words, deviations from ideal behavior. And basically the question we're asking is, under what conditions does the ideal gas law fail? So this is from Chapter 6.9 intro. We're going to ask, what is a real gas, and how does it differ from an ideal gas, and under what conditions does the ideal gas equation fail? So a real gas is pretty much every gas you know about, but how does it differ from an ideal gas? Well, if you recall, an ideal gas, we had a couple of assumptions that we made about it, and one of the key ones is there's no attractive or repulsive forces acting between molecules. And you also might recall when we introduced that assumption, we said that's not true. I mean, molecules are made up of protons and electrons. So if you have two gas molecules, one of them's got plus charges and it's got electrons around it. It's got plus and minus charges around it. So when these guys come near each other, the protons from one can feel the electrons of the other. They're going to get attracted, those protons are going to get attracted to those electrons. These electrons are going to repel away from each other. And if we get them too close, the protons are going to repel away from each other. So that, from the very beginning, this assumption is not correct. However, if the molecules are moving fast enough or they're far enough away from each other, then these aren't really that important. Remember, they're elastic collisions. They're moving quickly, then they smack into one another and move away. Then we can kind of ignore these attractive and repulsive forces. Under the conditions we're interested in, how does it differ from an ideal gas? Under what experimental conditions does the ideal gas equation fail? What we're looking for is, when do we end up with a situation where the molecules get very close to one another and they're no longer moving very fast? Okay, if they're moving fast and have a lot of kinetic energy, we can ignore the attractive and repulsive forces. However, if they start moving very slow, and if they get pushed too close together, they're going to start feeling these attractive and repulsive forces. So the way I like to think about that is I use the ideal gas equation as my starting point, PV equals nRT, and I like to rearrange it this way. P equals N over V times RT. And if you look at this equation, you recognize N over V, that's the number of moles divided by the volume. That's actually a concentration term, right? Molarity is moles per liter. So this term right here is actually a concentration term. We have pressure and we have temperature we can worry about. R is a constant. That's not going to change. So in other words, we have three situations we want to consider. We want to consider changing pressure, changing temperature, and changing concentration. So let's take these in order. Let's say pressure. If we were at a very high pressure means the molecules are all getting squeezed in together at a high pressure. And so if the molecules are squeezed in together, they are going to begin feeling the protons and neutrons and electrons of each other. So in other words, at high pressures, the ideal gas equation fails. Low pressures, molecules are far away from each other. They're not forced into a situation where they're near each other. So at low pressures, the ideal gas equation is great. When we go to higher and higher pressures, they begin to interact more and more. So the ideal gas equation begins to fail. What's the effect of temperature? Well, the effect of temperature is, at high temperatures, we said the high temperature, the kinetic energy is directly proportional to temperature. So at high temperatures, that means the molecules are moving faster, which means they have less time to interact with each other. So high temperatures, the ideal gas equation works great. It's at low temperatures that we begin to deviate. So what I'm writing right now is, I'm writing the conditions under which the ideal gas equation fails. So far we have high pressures, low temperatures. Now let's deal with concentration, N over V. Okay, so at concentrations, if you think about it, at a low concentration, the molecules will probably be far away from each other. If you remember, one of the assumptions of the ideal gas equation was that the distance between molecules was very large compared to the size of the container. Well, what if we put more and more molecules in there? Then that every time we put another molecule in, the distance is going to get less, or statistically is less. So therefore, at high concentrations, there's more chance to interact. So here's my three conditions then. High pressure, low temperature, high concentration. Under those three conditions, the ideal gas equation fails. In other words, we cannot use this equation. Now there's another equation, Van der Waals equation, which is a modification of PV equals nRT. And I'm not going to expect you to know how to use it. I mean, it's in the book, and if you want to look at some problems related to it, you can. There's basically some fudge factors you can use. It's a function of what different type of gas you have, and it's also a function of the conditions that you're under. But we're going to use PV equals nRT for most situations, but I do want you to know the conditions under which it will fail and which you would have to use the Van der Waals equation. Here's some data just sort of showing you what this effect is. It's actually a pretty big effect. So this is pressure. 0, remember 1 atmosphere would be like what we're experiencing right now in the lab, so something like that. And this is going up to 1,000 atmospheres, which is a very, very high pressure. Here's a bunch of different gases, and this is plotting PV over RT, and 1 would be an ideal gas at all conditions. And you can see that no matter what the gas is, there's a significant deviation away from that ideal gas. But the other thing I want to point out is the magnitude of this deviation. This would be a 10% error, this would be a 20% error, this would be a 30% error, this would be a 40% error. So if we were out here at 600 atmospheres and we were using helium, we would see like a 35% error if we used PV equals nRT to do our calculations. So that's clearly not good enough to do a calculation with. Even the ones that don't deviate as badly, like let's say something like argon, is still like a 15% error once we get up here at 600 atmospheres. And you notice some of them, like xenon, actually cross back the axis at 400 atmospheres. But as soon as we get away from close to 1 atmosphere, it begins deviating quite a bit. So you can see how high pressures have a very significant effect on the ideal gas equation. So let's take a look, next slide, we're going to take a look at just a couple of questions, see if you can answer these yourself. All right, first question. Given the assumptions of the kinetic molecular theory, how would the description of a real gas by the ideal gas law depend on the concentration of the gas? So gas concentration is not important. We just said that was not true. Best for a concentrated gas? No, it's best for a dilute gas. The more dilute the gas, the more the real gas behaves like an ideal gas. Okay, so this problem is going to be best for a dilute gas. Next question, a sample of methane is at 50 degrees C and 20 atmospheres. Would you expect it to behave more or less ideally if the pressure was reduced to 1 atmosphere? So this should behave more ideally. As we go to lower pressures, it behaves more ideally. Next question, the temperature was reduced to minus 50 degrees C. So we're at 50 degrees C, we go to minus 50 degrees C, the molecules begin moving slower, which means they have more time to interact, more opportunity to interact, so therefore the gas behaves less ideally if we reduce the temperature to minus 50 degrees C. These are the types of conceptual questions I expect you to understand based on deviating from the ideal gas law. I do not expect you to necessarily do calculations using the Van der Waals equation, but I want you to recognize the conditions under which the ideal gas equation fails. That wraps up Chapter 6 on gases and gas laws, and I thank you for watching.